whose width was continually changed. So you had this conductor whose width is W, length is L. The length itself is short enough that it's ballistic. In fact, these are what people call point contacts. These are extremely short. And the width is controlled by controlling the potential on the two sides, which we don't need to go into these details. But the way it was done is, by putting a voltage on the two sides, you could actually pinch in the channel or make it wider. So that's the x-axis. It's the width of the conductor. And if you look at the conductance is plotted in normalized units. Normalized in the sense that what is plotted there is this conductance divided by Q squared over H. Actually, what's plotted is not conductance over Q squared over H, but divided by 2Q squared over H. And this 2 has to do with the 2 spins, which I'll come to in a minute. But conductance is plotted, this normalized conductance, and what you see is it goes in steps. That is, goes from 1 to 2 to 3 to 4, etc. And the interpretation is that there's a two-dimensional conductor, so the relevant place to look at is this one. And ordinarily I might have thought that as I change W, the M should be changing continuously, but what it is doing is it's showing this integer, that it only goes with integer values, 1, 2, 3, etc. And that's what this experiment shows. And the reason we have the 2Q square over H is because of what I had mentioned, I believe, a couple of modules back, namely that for any conductor, there's always these 2 spins, you see. There's an upspin and a downspin, which can be viewed as parallel channels. And so, it is like conductance. If you don't worry about spins, you calculate something, but then there is an equivalent channel carrying the same amount of current, and so the conductances sort of add. The currents add, conductances add. And so, the conductance, if no spins were involved, then we would have expected that conductance normalized to Q squared over H should go as 1, 2, 3. But then because of the spins, if you had normalized it to Q squared over H, it would go as 2, 4, 6, 8, etc. Here in this plot, it is normalized to 2Q squared over H, which is why it goes 1, 2, 3, and so on. So what this experiment then shows very clearly is it's like the basis for this whole viewpoint in a way. So one could say that, as I said, this whole viewpoint arose with the rise of mesoscopic physics back in the late 80s. And this was one of the very important seminal experiments, really, which gave solid grounds for this way of viewing transport, of viewing current flow in terms of this, the ballistic conductance being this Q squared over H times the number of modes. Now, one thing you might wonder is, well, why do I have to go to, say, small things to see this? Shouldn't you be able to see it even with much larger conductors? So, for example, instead of going 1, 2, 3, etc., couldn't you be going, say, conductance versus width of a relatively large conductor, and couldn't you see something like this, where this may be, say, 997, that could be 998, that could be 999, and so on. And the answer is that, well, remember that the conductance we are calculating is at a given energy. So it is at this energy, let's say. And one of the points I had made earlier, something that I've usually, for clarity, not been writing explicitly, is the actual conductance is an average over energy. So in other words, we are talking about this conductance at a given energy, and the actual conductance would be obtained by averaging it over a certain range of energies, of the order of the voltage that is applied and the kT. And if, let's say at some energy it happens to be 997, another one it happens to be 998, another energy is 999, what that means is that at normal temperatures, when you measure this, you might actually get a fraction just because of that averaging, you see. And that is what would happen lots of times if you actually did this experiment at not very low temperatures. So this particular experiment, for example, was actually done at 4 Kelvin. So yeah, I believe that was the temperature, or could be a little lower. So it is done at low temperatures. Whereas, if you had looked at room temperature, for example, it might have all gotten washed out because of that averaging effect. And another interesting point then is that this experiment was actually done in a semiconductor. In a semiconductor where relatively the electron density is small. And because the electron density is small, you see these number of modes, that's also relatively small. So what I mean by that is, if you look at E versus P, in a semiconductor we are talking of electrochemical potentials that are way down here. And so this P is small. What that means is you have a big de Broglie wavelength. And so for a given width, the number of de Broglie wavelengths that fits in, this is a big thing, so that's a small number. Whereas if you are doing this with metals, then often the electrochemical potential will be deep inside here. And the de Broglie wavelength in metals is often of the order of atomic distances. So what that means is, if you had a conductor whose width was 100 atoms, you'd have about 100 modes in metals. On the other hand, in semiconductors, usually you'd have far fewer modes. And so this first experiment showing this quantized conductance, that was done in a semiconductor, I believe gallium arsenide. But since then, during the 90s, people have done these experiments on all kinds of things. So especially one that's quite common nowadays is the metallic Breck junctions. That is where you take a metallic wire, just take this metallic wire, and you gradually pull on it. And when you pull on it, what happens is some region becomes narrow, which is where it eventually breaks. And so you call that a Breck junction. But as it gets narrower, what you see is the conductance goes down in steps just like that. And finally till it breaks off, at which point, of course, the conductance goes to 0. So even in metals, people have seen this. So people have seen this now in all kinds of different materials. And it is usually interpreted as, again, this idea that the ballistic conductance should be Q squared over H times a number that tells you the number of, this is called the number of modes, which tells you essentially the number of channels. So conceptually, I almost think of these M's kind of as these lanes on this highway. That is, how many lanes do you have for electrons to go from left to right? And if you want the conductivity, then of course we can use this relation that we had last week, that conductivity is ballistic conductance times the mean free path. So now based on this new form for the ballistic conductance, which is Q squared over H times M, we could write conductivity is Q squared over H times M times the mean free path, and then of course the dimensional thing, the 1 over W or 1 over A is needed. So this would be I'd say the modern view of conductivity, the way to think about it. What determines conductivity? Well, first thing is, how many channels do you have? M. How many channels do you have for conduction? Those are like the lanes on your highway. And what is the conductivity? Well, it depends on how many channels you have and how easily you flow. That's the mean free path. You see? That's M times lambda. And this M is determined by this number of wavelengths that actually fits into the cross section. So this is how we'd look at conductivity. And the point I want to stress here is, again, the importance of this experiment. One of the things that I often stress is that, especially with people who do theoretical work, is that in our field, experiments are really extremely important in terms of clarifying concepts and establishing validity. Because one of the things we saw was back in the 80s, there was enormous controversy and argument about what is the resistance of a ballistic conductor. As I said, freshman physics said that resistance is resistivity times length. It's proportional to the length. And one of the nice things to argue about was what would happen if you reduce the resistor and made it so short that there was essentially no time for electrons to get scattered, so that you had ballistic transport. What would be the resistance? And there's lots of arguments on those things. And what essentially settled everything was this experiment, you see. So just one experiment actually can help, in terms of giving a perspective and solidifying the basis for this whole viewpoint. And what I often stress is, whenever people tell me that they have a model for quantum transport I always say the first thing you should try is model a ballistic conductor and see if you get quantized conductance. That's the first step. If that doesn't work, then it's really not much point going further. Whereas, this is the bottom-up view, where I say, start from that simplest thing, the ballistic conductor, and make sure you get that right. And then one can put in the rest. Whereas the conventional view usually has been the top-down view, where you start from big conductors and then try to understand the small things. And what I feel is the bottom-up view, and that's what I've been trying to stress, actually gives you a much clearer understanding of the transport process and how devices work and how electrons flow.